The second application we're going to look at is volume. You should be familiar with the volume of revolution when we work in rectangular or Cartesian form. Delta x is always taken to be small, so that the element here, just as it was with area, is approximately rectangular, with a height of y and a width of delta x. So this is the element here once it's been rotated. It's going to give us a disk or cylinder, the radius of which is y and the width of which is delta x. Therefore, the volume for that element is pi y squared delta x. Now, when we apply that and add up all of the disks from A to B, we get this integral. We integrate from x equals a to x equals b, pi y squared dx. Now if we go to polar coordinates, the origin is here, and we can see the initial line going off in this direction. This is our element. We consider it to be approximately triangular. And if you look at the coordinates of Q and the coordinates of P, we can see that this length is r plus delta r, and this one is r. The angle here is delta theta. So the area of that, using the formula half AB sine C for a triangle, is going to be a half r plus delta r and sine theta. Now, there is a theorem called the theorem of Pappus, which says that the volume swept out is equal to the area of the element, which we've got up here, multiplied by the distance moved by the centroid or centre of mass of this shape. Now, since this is a triangle, that is at 2/3 of the distance across the triangle, which we'll take to be r, since we're working with very small sections here, and therefore delta r eventually is going to be considered negligible, and that distance therefore is 2/3 r. And that means that if we form a right angled triangle here, this is 2/3 r sine theta. When we rotate that around the initial line by 2 pi radians, the distance moved will be 2/3 r sine theta times 2 pi. So let's think about the area of this element again. The angle in the middle there is actually delta theta, so this one will be sine delta theta. So that's the area of our element, and this is the distance moved by the element. Therefore, the volume swept out by the element is going to be a half r plus delta r, sine delta theta, multiplied by 2/3 r sine theta times 2 pi. The half and the 2 from the 2 pi will cancel. So we get 2/3 r squared, r plus delta r, sine theta, sine delta theta. And I almost forgot the pi there. Let's put the pi just here. The next thing to remember is that we always tend the delta theta to 0. And that also means that the delta r will tend to 0. But sine delta theta tends to delta theta as delta theta tends to 0 is something else that we can use here. You may be aware of sine delta theta over delta theta tending to 1 as delta theta tends to 0, which means sine delta theta tends to delta theta. And that means up here, what we end up with, and this is obviously going to be an approximately, because it's in the limit as delta theta tends to 0, but it's going to be 2/3 pi. We're going to get r cubed, because we'll consider the delta r to be 0, sine theta, and this one will just be delta theta. And that is what leads us to the integral here, where we integrate between theta 1 and theta 2.